Hello, everyone. Thank you very much. That's fantastic. Thank you for the opening and brief introduction. And I guess I will pick up from here and introduce myself a little bit. First of all, thank you very much for joining me here tonight, or today, wherever you are. And I've seen a couple of, I can actually see the attendees a little bit, and I've seen a few friends of mine and colleagues and even customers. I have been a shout out to those that know me and have met me before. Otherwise, I'm pleased to meet you all. I'm hoping that maybe during the next conference or so we can actually talk in person. So if you're here tonight and you're happy to talk about what I'm presenting today, and you're going to say the Hadoop World coming up in November next month, and you would like to talk about this and other HBase related or even Hadoop related topics, feel free to just talk me up, and I'm happy to answer whatever I can or throw in my 2 cents to any of your questions, so please do so. So for today, I picked a topic called HBase Schema Design, which is close to my heart because whenever I go to customers, I sort of see a recurring schema. So I'm thinking that HBase, similar to databases and even programming, has this sort of recurring patterns of design that you often see if you handle the same problem set. You have these recurring patterns, and I think one of the basic topics, one of these patterns or types of patterns that you have to deal with is how do I design my schema for HBase or for a database or whatever it is. And I think that there's a couple of things that I can share or just would like to talk about that might be of interest for you as well. So let's get started. First thing, quick one about me. I'm a solution architect at Cloudera and HBase committer, also a real committer, not too active there lately, but I had a good reason for that, which you can see there's the horse and the book. So I was busy the last 6 months or so in a cave and trying to finish this book called HBase, A Definitive Guide, which is now available. And so if you want to go deeper into these topics, then please feel free as well. Go read the book, because most of the pictures I have here are in the book as well, having text left and right, so hopefully that helps. Working with HBase since 2007 and organized the Munich OpenHUG User Group. I'm sort of most of the time here near Munich and help out here. And speaking at different conferences. I was at the FOSDEM conference in Brussels, and going to speak at Hadoop World next month as well. So, and there's some book signing. I mean, if you're interested. So I don't know. Now for the overview. As I said before, I think schema design is quite vital when you want to implement a good solution. Anything that you want to have run in a hopefully optimal performance or setup. Schema is one of the really crucial part, especially with at HBase, because there's a couple of things that HBase does not tell you up front, but you need to know as well as you go forward. The design or schema design in itself is nothing new. I mean, you know this from RDBMS, from normal relational databases. You have to somehow design the schema. Sure, you can start with like a table, single table, that's fine, and you had another one, and then over time you realize maybe I should have normalized in my relational database model. I should have done this and should have done that. So over time you basically adjust your model, and that similar thing happens with HBase as well. But if you knew a few things before you get started, then you might just basically not fall into certain pitfalls and be able to avoid a few things on your way. And I think that's basically the topic that I want to cover today. It exposes architectural and implementational details or features that you have to sort of just take for granted, or, I mean, it's open source. Please, I can only say please help contribute. I'm sure a couple of those listening right now already contributed code to us, to the project, and us, I mean, you and me and all the other committers and contributors. It's a great, great project to be on HBase. Great people. All the committers I know personally are great, great people. Know most of them for a few years now, and I wouldn't miss a day. They're really just great people. So if something isn't working and you don't like it, please feel free as well to change it or so if you want to, or discuss a change. Bring it in, and it might be worthwhile. Also, some of the things that we discussed could be handled in a different layer. So think about Megastore or Percolator. These are two papers that came out of Google that would discuss how to use Bigtable as their basic storage system to handle, for example, transactions or transactional type sort of across tables or rows, updates or optimistic transactions rolling forward only and stuff like that. So some stuff you can just do in maybe the application layer or having a storage layer in between where your application just writes to it and your layer in between can abstract this. But sometimes you just have to write this straight in code and just either deal with it or write your own layer in between. Let's start with sort of like a high-level picture of the architecture. If you look at basically the sort of schema, it's very simple. We have HBase there, and HBase has a few foundation blocks, which is HDFS and Zookeeper. And what you can see is that you talk to HBase through an API. There's a master node, region servers, and within the region servers you have the actual storage files. You have a in-memory store and a write-ahead log, and a few other components. So in detail, basically, why using HBase? Why using HDFS? HBase uses HDFS because it gives it what it needs to rely on. It gives it the checksumming, the replication, the failover, the scalability in terms of being able to store an endless amount of data, like virtually without much limitation. And the reason why it shows HDFS is because it comes out of the same sort of where the rest of the Hadoop project came from. I mean, it's all the same sort of people involved. Duck cutting was like building back then Nudge and added this HDFS as an open source implementation of GFS and then MapReduce, and then the same sort of team threw in why not also do Bigtable on top of GFS. Why not do it the same as HBase on top of HDFS? So it very naturally sort of goes together. Someone asks if there's a problem with the session. Everyone else can hear me? Just to sort of confirm that everyone is aligned. Smina? Okay, cool. Yep. Some can hear, some don't. So if you can't, then please. I don't know, check your connection or your speakers. Fantastic. So now back to the storage layer. So HBase uses HDFS, gives it everything you need. You could run HBase on top of a different file system if you wanted to, but it should give the same guarantees. Otherwise, you're on your own. So you can actually run HBase as it is today, just unpack it and run it on your local file system, but you have no guarantees. So if the file system goes corrupt, your data is gone. So you have to have something that you can rely on. The native API that you could see in the picture earlier is basically Java, but there are gateway servers for REST, Swift, and Avro. And based on that one, there are other languages on top of that use these interfaces, DSLs and other sort of higher level abstractions where you can talk to HBase through a layer of different helpers like gateways that use REST or Swift or Avro underneath, and then talk native Java to store and retrieve the data. The master that we saw in the picture just manages the cluster. It has nothing to do with the data. That's what the region servers are for. So region servers are the ones that manage the data. So if your client is going to talk and wants to have some data, he has to first find the region server that manages the data, and then talk to the region server directly. That's similar to HDFS, where the client talks to the data node, and the name node is the orchestrator, or conductor. So you have sort of a very similar setup, and most of this architecture is basically borrowed from Hadoop in this case. And finally, there's Zookeeper underneath, which is sort of the neural network. It's crucial for HBase, bootstraps, and coordinates the cluster. Without Zookeeper, there is no cluster. So that's a very crucial part. Doesn't need much in terms of resources, but if it fails, then you're really in trouble, basically. So that's sort of the high-level view of the architecture. leading into that is basically why I started with the architecture there, is that you have to understand one thing about HBase, or the big table design or model, is that when you have a table which is always a sorted list of rows, these rows are actually split into what is called regions. So if you look at the picture, you can see here that there are ranges of rows, for instance A to F or G to L. I can't barely read it, it's small, but then you have to basically see that these basically get distributed over to the different region servers. So the region servers on the right-hand side serve that. So that's basically how that is split up over regions. And the next one just shows that I like slightly different view on how things work, is that the rows basically get randomly distributed. These ranges of rows, these regions, get distributed over the different region servers. So you can see here you have regions with distinct ranges of keys in different areas. So this is important later on when we design the schema, because that has a crucial impact. So we were talking about currently the architectural part of the system, and you will see in a minute how this influences the schema design. That's the weird part about HBase, I think, to a degree, that when we talk about architecture right now, it does have a strong impact on the actual schema design. But you need to understand this just as on a high-level view. So the crucial part is here that we have an auto-sharding and a distribution of these regions. So the unit of scalability is the region. It's a set of contiguous rows, and it's spread across these region servers. The reason is also that it can be moved around for load balancing and failover. So that's sort of the core idea about scaling in HBase. Automatically shards and distributes these across the servers. And the capacity is basically just a factor of how many regions you have per nodes and how many nodes you have. That's sort of the trick behind scaling, is just adding more servers so that you do not have too many regions per node. The next thing that you need to understand about the architecture, which influences greatly the schema design, is that data is broken into separate, distinct directories on disk, which are represented on a higher level in the design basically as column families. So column families give you the sort of opportunity to break data into separate, complete distinct areas, which are handled separately as well. So if you look at the reason for that, is that if you have separation of data, then you can do similar things what columnar databases do. You can query these sort of subsets very quickly, as opposed to scanning entire rows. It's not a new idea, being able to split or aggregate or focus on a certain particular number or set of columns. Columnar databases usually do this per column. Here it's basically a number of columns. The other part about column families, they give you a choice of what you want to do with the data. For example, you can specify no or a specific type of compression that, again, when we talk about schema design, you should think about this, because it may help you squish more data into your cluster. So being able to specify certain attributes per column family might drive your schema design in a certain direction, because you can use this later on to more efficiently store your data. Information is segregated based on the access pattern. So depending on how you want to query data on, you have to sort of think about how you partition. And the data is stored in one or more storage files called H files. That's also another architectural thing that, if I go back for a second to the previous slide, if you look at the bottom now at the HDFS, the sort of light blue sort of box at the bottom, you will see that each column family, the pointer's going downwards, actually showing multiple yellow and purple boxes there, or pink boxes. Sorry, the color scheme, I came up with that, so it's probably not the best. But anyhow, the yellow boxes should, in this case, just represent compressed files, and the other one, the pink ones, uncompressed files. But you can see that every directory, which is the very low the bottom information there, saying where the data resides, is that each column family consists of multiple store files. They result from something that comes out of that log-structured merge tree heritage of a big table, where data is aggregated in memory and then flushed out in larger chunks onto disk. So it's basically aggregating, flushing, and then there's a background process waking up called compaction, which then says, oh, I have too many small files, take a few and rewrite them to a slightly bigger one, like combine 10 to one large one, and then it goes forward in the background, flushing, compaction, and creating these files in the background. Again, we need this in a minute. Let's go forward. Now, when I talked about that we have multiple store files on disk and column families are separated, how does the system actually read? Again, this comes from something called this log-structured merge tree, where it has to do a merge read, which has to basically go through and say, okay, each store file could have some information that pertains to a row, because I could store column A now, and in 10 hours I store something column C. And because in the meantime the system has already flushed out data to disk, you have store files which hold, all of the store files might hold information across all of these files that make up one row. And if you look at the row here, you can actually see that's the yellow part basically is the row, that even in a single store file you might have multiple entries that pertain to a row, because if I am updating the column 10 times right now, then all of these 10 updates are currently held in memory, or 3 by default are held in memory, so that when I read the row, I can actually look up those directly in memory. But to really know what the row looks like, I have to go through the in-memory information and to the on-disk information, look at everything, and then decide what I can do. Remember in this picture, or look at this picture and look at this blue box called BF at the bottom. That's not best friends here in this case, but it's actually Bloom filters. So the Bloom filters we will get back to in a minute. But the system is smart enough to know, okay, there are multiple files, and these files are in separate directories per column family. And when I want to, when someone asks for the entire row, I have to go to these multiple directories, look at all of these files, find the information that basically is currently active or is part of the row that I'm asking for, merge this with the in-memory representation, what's the information that is available there, and then return the row. You can see in column family 2 in this case, for example, the mem store has nothing that pertains to the row, therefore it's basically being skipped. So that's how it does that. The Bloom filters, the BFs there, they're generated automatically when the file is persisted to disk. So in memory, there is no, in memory when the data is aggregated as you write to it, there is no Bloom filter. But once the file gets flushed to disk, the system adds a Bloom filter. Again, that will be useful in a minute. The Bloom filters here is, they are stored at the end of the file. They add to the file size. Therefore, you have actually two sort of choices. You can do this on a row level by row key. So in the Bloom filters basically index all of the row keys, which means you can ask for a specific, you can ask a specific filter for a file and say, do you have this row key? And the filter would say no, or I may have it. And if you may have it, you have to check, and then it might be wrong. And there's a 1% by default or so error rate that it's wrong. But in 99% of all cases, it usually says yes, I have it, and it actually has it. And if it says no, then you certainly don't have that row key. You can also combine the row key with a column key, which means you can combine the two keys and say, now I know not only that the row exists, but if a specific column exists in a row that I'm asking for. But you're adding more overhead, obviously, because you have to store many, many more entries in your filter, so the filter gets larger. You have more data that you have to store at the end of the file, and because they get loaded into memory when the file is opened, because you want to query these filters very quickly, then you have trouble that they may not fit into memory. I know from other committers in my other peers, basically, that they had to switch from row column back to row because they were just too large to hold in memory. Then what this can do now is that you can filter these entire set of files. So you can actually say, do I have to actually read, or don't I have to read from a specific file? And they're also useful when you have many misses. So if you expect from your reads that random reads that you like a cache, for example, and you do not know if the key exists or not, then they're also useful, because then you can quickly say, no, there isn't anything in here, so you can move on. This looks like back to what is on disk. Think of this as one column family here. Again, we have a set of files. That's how they are stored on disk. And each of these files has the Bloom filter is stored as part of it, and has a block index stored with it. So the block index is the one that indexes into the file. And as you can see, if I have only the block index, then I have to really go through and do 6 seeks and block loads in each file and get 64K by default out of these files to check, does this file actually have something that pertains to this row? Because it's quite unlikely that I'm asking for a row key that matches the block boundaries, because the block index is quite coarse-grained on the start row key of the block. And in 64K, you could squish a lot of data in. So you often have the block index say, yeah, there's a block that might have this key, so you need to get the block into memory and actually read this. And that causes churn on in-memory block caches and things like this, and I/O that you can avoid if possible. So there's this Bloom filter, if you can see at the bottom. If it says, no, I don't have anything in this file, no, not in this file, maybe in this one, most likely it's right, not on this, and maybe on the last one, then you have only 2 block loads. So you're bringing it down from 6 to 2. Block loads, 64K into memory, cache churn, whatever, is reduced by tremendously. So in this case, by whatever, 33%. And depending on the size of the system, this can tremendously help reducing I/O. Again, that's something when we get closer and when we get to more to the schema now, that is important. Now here comes a more complicated one. So you understand. I explained it now that how files basically are stored. So you have like multiple files in a directory per column family. Now, what you have to, the last thing to understand before we can talk about how to design keys or like row keys or column keys for HBase is you need to understand how they're actually stored on disk. On the top left-hand side of this picture, and I call this sort of process fold, store, and shift. So I should have a TM at the end or so, because I think I like it, but it might not make any sense to you. But let me explain what I'm talking about here. So on the top left-hand side of that slide, you see the logical representation of a table. You have the rows 1 to 6. You have column families, CF1 and CF2, and in each column family, in the red one and in the yellow one, you have 2 columns here. For instance, column 1 and column 2, and both have a column 1 and column 2, so it could be anything basically. And you can also see with the duplicate boxes there that row 3, for example, has 3 versions of column family 2, column 1. Versions in this case is just that the third, this is why HBase is called multi-dimensional, is that you can also not just store one particular coordinate, but you can actually store them with a time dimension. So you can have multiple versions of a cell, which is quite interesting if you want to keep, for example, the last 3 copies of a downloaded web page, like the crawler do that, so that you can go back and then do a MapReduce job and say, okay, how has this changed over time, and do machine learning on it and lots of other interesting things. But that is sort of like how it looks like logically. But if you can and then fold this thing, it actually says, okay, every column family isn't really multiple columns. We are just one directory. So all of the columns just get moved into a single sort of column, which is just pushing them all into order by time in this case. So you see how the red ones and the yellow boxes are squished over to a single column. It's on the right-hand side of each of these 2 boxes on the top right-hand side of the screen. Now that's basically the sort of the folding of the table into a single column, and then it gets stored on disk. So the store parts, actually that's how it looks like in your file. So if you dump a H file, an HBase H file, every single value that you store, which is like one particular column and with one particular version, is actually stored as a separate row in your file. So these rows, these logical rows, become single value rows in your storage files. So they hold everything that they need to identify themselves. I call them coordinates. So these coordinates are the row, the column family, the column qualifier, the timestamp. Timestamps are the versions because that's currently how it's done. It just uses the system current time millis in this case to store the version, but you could use custom versioning there as well, and the actual value. So that's how it's stored on disk. So there's a lot of information for a single value in your system, but it's self-contained, so it can actually be identified completely by its coordinates. It can be moved around by the system, so it makes the maintenance part in the background quite easy. And keep in mind, we talked about compression earlier, because there's a lot of repeating information in these, and as these compression algorithms, LZO or Snappy, they have these sliding window that they use to compress data. They're quite good at actually finding repetitive data and compress them quite efficiently. And there's also Jira Open out there that talks about and works on prefix compression, that we can take these things even further and reduce this quite well. So it looks like a lot of overhead, but it combined with compression, not so good, but combined with compression, it stores quite well. So that's basically how it's stored. So every value basically is a row, a single column row on disk. Now when you look at the final step of this picture, that's the shift part on the left-hand side, bottom left-hand side, that's actually what you have to understand is that when you move data around in your schema, in your rows, like when you design how you actually store data, it doesn't matter really where you put the data mostly. So you can actually have in the first of these reddish sort of, no, it's I don't know, some light red color or orangey, that has the value on the right-hand side. So it has the row, the column family, the column qualifier, the timestamp, and then the value. That's the typical way to store that. But then look at the next row down, where the middle one, where we move the value from the value part into the column qualifier. Like the C1 is attached to the value. It's the same amount of data that you store on disk. It's just shifting data around within that same row. So nothing changes. And then the next thing is we're actually moving it from the column qualifier even further into the row key. So you have, that's sort of like the big step, I think, to understand with design is that you can actually use the row key to carry pertinent information of the actual row. And in this case, if you look at this row, it has no value at all, like the one above. So that would be something where you have a row or a table which has really no column but a dummy value, which in this case just the 00, like the single byte 0, which I had to put there because if there is no value, there is no column. So I have to put something there, otherwise the thing isn't stored. But I'm just putting a single dummy byte in there. So that fold, store, and shift gives you basically the power in HBase to design your schema by moving data around within the schema. So there's a couple of places where you can put it, and we look into this in a minute as well. So I'm hoping this basically is a bit more clear now. A few more notes to this one is that you have to, as I said, you have to sort of see that the logical layout is not what the physical one is. So it's completely separated from that. It's stored differently, and therefore we can work differently. All of the values have their full coordinates. I mentioned this, and folds into this single row per column view. The interesting part is that nulls, so if you have typical nulls in a database, are cost-free because nothing is stored. I mentioned that if I don't put that null there, then there is nothing stored in the single column per value storage format. That if I put a null there, or if I have a null in a database table in a row, I can just omit that whole value. It's just not there. It doesn't exist, so nulls are for free, which is quite nice. And versions are just multiple rows in the folder table. So if I just quickly go back to that previous picture, just to finish this up, is if you look at the bottom right-hand side at that yellow box, you can see three versions there: row 3, row 3, row 3, with different shades of yellow. You can see that's exactly the same coordinates. The only difference is that the timestamp is different. And what you also might notice is that the sorting is interesting. All of these rows, all of these yellow boxes are actually stored ascending by row key, column family name, and column qualifier, the C1 there. So we have a row 1, then row 4, row 5, row 3, row 4, row 5, row 6, stored ascending. But if you look at the timestamp, that's actually descending. So we have a T3, T2, T1. The reason for that is when you query the database or query HBase, what you usually want is the most current value. And because we scan a block from, or when we load basically and we look it up, then we just have it basically so that we want to have the first one being the most current. It's actually stored in a way that it's stored ascending, but for the timestamp which is descending. So when we say, just give me that row with that column, give me that column from that row, from that column family, it just takes the newest timestamp, which is, in this case, just the first one it finds, because you do not specify which one. It doesn't know what the top one is, like what's the newest one you have stored. That's basically done that way by just saying, okay, let's give me the first, and that handles that one. Now, next step. Since we have looked at, let's go one more, go to this one. Since we now looked at that every column family is a separate directory, similar to columnar databases. You can basically filter out files using Bloom filters or a few other sort of choices. This sort of picture now gives you the key cardinality, like an overview of what you can do and where you should store information in your schema to make sure that you get most out of your lookups. So when you look at this picture, you have the full key up top. That's the same what you saw stored just before in your store file, which is the row, the row key, the column family, the column qualifier, the timestamp, and the value. It's exactly how it was stored on disk. You saw that earlier. But depending on where you put the information that you need when you do a read, that is crucial for where you put it in your key value. This is what is called a key value, the entire thing. And in this case, the further you go to the right, the greater the cardinality and the worse the performance. And if you go further to the left with your information that you look up, the better the performance and the lower the cardinality. So you can narrow down much quicker to find the information. There's a bit of a problem with this. Whenever I discuss this picture, I could have done differently because I chose the way it's stored inside the key value. So I chose row, column family, qualifier, timestamp. In reality, the timestamp is actually more important than the column qualifier because the timestamp has one additional quality. Each store file that we saw before has another value with it which says or records the newest timestamp of something that was stored in this file. So if you ask for something, okay, I want to get something from the last hour, you could just say, give me anything from, I don't know, until you find that you have succeeded that past hour. You just scan backwards and you find, okay, that's newer than what I want, and so you can stop somewhere or just do random lookups and then stop somewhere, which sounds okay when you do like your read or your read or access patterns. But in actuality, it can be quite bad with HBase because what happens is that when you have a timestamp and every file knows when it was written, then if you ask for something, I'm just really interested only what happened the last hour. If you then say, if you put this into your get or scan request, then the system that we saw earlier, the one that assembles the row, can say, oh, this file here was written 3 hours ago, and he's asking for something that is an hour old, so I skipped the entire file. So that is really good. Because over time, if you have a heavy churn on your system, if you build like a typical sort of database type system that does a lot of reads and writes, mixture, so in your system, then over time you will aggregate and build up a lot of store files. And the more you can skip, the easier it is on the system because you don't have to do these unnecessary lookups. So two things you can do is you can either use a Bloom filter to say, okay, I don't want to have this file, or you can use the timestamp and say, I want to only have the last hour, therefore I can skip anything else. So these sort of things, they are really important. And but as I put them in the right order. So timestamp should actually be one to the left. Now, what can you actually do? If you have something in the row key and you're asking for a particular row key, which is the lowest cardinality, the highest performance, because then the system can do a straight lookup, find exactly where you want to look for something, and assemble the details. That's helping you skipping entire rows because you're asking for a specific row key. Therefore, it's really good to skip entire rows. It also helps you skipping store files and the filter compatible. I address it afterwards. The next step down is column families. I mentioned column families are separate directories. So if you do design your schema, if you keep your data that you query together in column families that you query together, then you can skip entire other column families that you don't need for that type of query. So you can say, okay, I have a column family A and column family B. A is the metadata, and B is the content, the actual HTML pages for my crawl. In this case, then you can achieve it that you can scan the metadata to, for example, find out how many data have I downloaded by just adding the size field or size column of the metadata column family, and just ignore the entire big HTML column family. So you're much faster doing things on that smaller column family. So that skips basically. That can basically help you skipping store files because you can mask out entire directories. So as soon as you basically move data or there's things that you query for from row into column family, you're losing a little bit of granularity, but you can still basically mask out entire files. And when I talk about looking up or moving data, so we get into this in a minute, so just keep this in mind that try to keep data in the row key, but you can move it out to the left, or if you want to keep it all basically in the value. But if you put everything in the value that you're looking for, then the only thing that will help you is the last thing in this picture is the filter, which is not really as potent as you would think it is. The filter is nothing else but a helper that on the server side can filter out details so they're not getting sent back to you to say, no, that's not what I want because it doesn't have the value that I'm looking for, or it doesn't have the column name that I'm looking for. So the filters basically help you masking things out on the server side. But the server still has to do the same work. It has to scan through and filter everything. So that's basically keep in mind. The filters are a good thing, but they're not really for high performance things, so high performance querying. It's just helping you reduce network traffic. So basically, that's the cardinality here. Best performance gained from using the row keys. So if you know exactly what you're looking for, that's the best performance. If you don't know what you're looking for and you have to look at the values, that's the worst. Time range bound reads can skip the store files, and so can Bloom filters. Selecting column families, a reduced amount that has to be scanned. So that's basically wrapping up what we had just then. Now, the next sort of thing that you have to think about is that, okay, back to the logical view. We know that the table basically looks a certain way. So how can we basically make sure that we design right? So you can either design something where you say, I move everything into the key, and you have what's called a tall and narrow table, or I move everything basically into my columns and basically use the columns properly so that I have like a row for, say, we're talking about an inbox here. Say my row key is my username, and all of the columns hold my email. Then I have a flat and white table because you have these outliers possibly that have thousands and thousands or even millions of emails in it that you have to somehow deal with. The problem here is so that rows do not split. So when we talked about earlier that we have these regions that split, they can only split at row boundaries, which means if you put something in there that is huge, you might end up with a one-row region, which that's just what it is. If you set your region size to 512 megabyte, you have someone with lots of attachments or whatever, you easily go over that one, and that's probably not what you want because then there's no splitting and there's no performance. This heavy thing has to be lifted around, not a good thing. So that's something to keep in mind. It has the same storage footprint, so you can actually move them around. But on the other hand, you have to be sure that when you move things around, you may have to put in this dummy column there on one hand side just to be able to save it at all. Though the good thing is you can use partial key scans to actually look it up. We get to this next slide. Tall versus tall is good with scans. Wide is good with gets. Okay. And atomicity is a problem there because atomicity in HBase is only on the row level. So if you were to store my inbox in multiple rows, so I keep the table basically narrow, then I cannot update the entire inbox of mine with an atomic operation. That's sort of the thing that you have to keep in mind. Sure, we have locks, but locks are not good. You shouldn't use them, and therefore, well, not in general, you can use them, but you have to be careful because they have like a lease time, and if your client fails, then the next one has to wait for the lease time out. But you're only locking one inbox, so it's something to have to decide on. But yeah, that's basically sort of the question there. Then large graphs can be stored in adjacency metrics, for example, to do this in a table there. Then the next thing here is an example. That's the inbox there. So we have that. You see my emails there. There's a user ID. I have a data. It's my column family. The message ID is my column. The timestamp and the email message, basically. So that gives me the entire sort of storage layout on disk. And you can see here in this example, I have the typical setup where I have a single row inbox, which is the top one. All of the row keys, which is the user ID, is the same. I just have different columns, which are the message ID. And the timestamps, I don't care because I only store rolling forward, so they just move forward. Or I move, for example, here the message ID into the key. Now I have a compound key, and that compound key is the user ID and the message ID, which then is the same storage requirements, but I have moved pertinent information that I otherwise have to scan either by looking at the row into the key, so it's good for accessing it very quickly because I have a higher cardinality. It's good that I have now something that is easier splittable, but I lost atomicity, so that's sort of to keep in mind here for any design for either of these use cases. The good thing is you can still access this data quite nicely because there's the so-called partial key scans. So what you can do is this. Have a look at this. The user ID with the key is the user ID. Then you can scan over the entire inbox. Basically, you get like an entire row, which is the inbox. But you can, because there's a in-row scanning as well, so you can actually iterate over each column. You don't have to materialize the entire row, which so there's a batching in HBase. You don't have to worry about that getting too large in terms of when you read it into the client. You only have to worry about it if basically you cannot split it anymore because of the size of the regions. But then you can see how I move more and more data into the key. I move the date in, or maybe the date and the message ID, or the date, the message ID, and the attachment ID. So what you get there, if you look at this, basically, you can scan over the attachments of a message for a given user ID and date, the last one there. So you can actually then, if I say, no, I don't care about the attachments, I just want to get the messages, basically, then you can basically just go to the second one where you say user ID and date. So you can find all of the messages of that user for a specific date by just taking this as the start key of your scan. The end key of your scan would be the same one where you just increase the last byte by 1. So you basically say stop at this next bigger one, which is exclusive for a scan, therefore only including exactly this starting key. But it will match anything in between, so you can iterate over every row in between and say, okay, the first thing I find are the message ID, and then the next thing I get are the message IDs and all of the attachments to it. So you can actually scan through and access anything you like without even knowing what is there by just being able to just set a specific prefix that you want for the row key, and then start the scan there, and then just iterate over and get just the next one and look at it. And as you get the row key, sure, you have to pass it back in. So there is a need to actually make this parsable, and there's work being done that this is actually an error record in the key, or for example, or some protobuf record, but you have to then make sure that the sorting order is correct and things like this. There's serialization formats that keep the sorting order and things like this. So there's a lot of ideas there to think about, but that's sort of the general concepts. And now look at this as another example, sequential keys. I mentioned them earlier. Sequential keys basically, I didn't mention. The sequential keys basically, what you do here is that you can put the timestamp to the left. So you just have growing keys, like the key just goes 1, 2, 3, 4, 5 going forward. Why is this a bad idea? It's because you're hotspotting on a region. Remember when I said the region covers a specific, distinct contiguous number of rows. If you're updating a row, which is basically writing forward, so an increasing sequential key, and is uniformly basically or monotonously increasing forward, then you keep writing to the same region over and over again, which means that you're hitting the same region, which means you're hitting the same region server, which then hotspots has to do all the work, and you can overload the system. So even if you have like 100 machines, and I've seen this over and over again, you can basically only get the performance of a single machine. So that's not a good idea. To avoid this is that you need to make sure that when you design your schema, that you actually distribute the keys proper over the different systems, so different regions. So the way to do this is either you do a sorting, you prefix the key with the timestamp with a distributed value to bin it or bucket basically the rows across the regions, so like some hash, for example. Then basically you ensure that this hash hits all of the regions. It has to be large enough. You could do this, what I called key field swap promotion. Switch these around. You saw earlier where I had the user ID and date. So instead of storing date user ID, I already had them swapped around. I just basically swap fields, or I move a field from a column information somewhere or from the value into the key saying, oh, I know this is a certain thing, and we will see at OpenTSDB how this is used. And the last thing is you could do randomization, and I have an example for that. Let's move on. So that basically just wraps this up, is that for sequential reads, sequential keys is good. Random keys is bad, because if sequential reads random keys, so you have to do random lookups. So that's not really good. And vice versa, if you write sequential keys, it's bad for performance. That's the yellow arrow there. But if you do random keys, it's really good because you're spreading your writes over all of these regions. In between somewhere lies the sorted keys or the promoted field keys. So design it properly so that when you have your load going up in your system, that you make sure with using Ganglia or just the UI, the master UI, to have a look at how many operations you have per server. Make sure that you just don't have one taking all the hits and then the other ones don't get any hits. So this sort of setup basically, or this sort of design is important. So the key design here is that based on how you actually how you write your patterns, it's either sequential or random, or this mixture using the sorted one, which goes towards the random. And often you need this combination, which is then to overcome the sort of problem that you're only writing to a single region. If you keep sequentially writing forward, then you might have to use sorting. You have to use sorting or using the key promotion. Neither is it necessarily bad. So if you really say, I need sequential keys, well, then you have to use bulk imports. Prepare the files outside and bulk import the data into your system. And then you can read it nicely sequentially, because that's what it's there for. Sequential in, sequential out. Same with random in, random out. If you have random keys and you do random lookups like a cache, then that's fine. Great distribution. It's not as great for reads, but then you have to just take the block cache either up or switch it down, so that you don't cache too many of these random blocks, because you never have a hit in the same block again. So a couple of things that you need to keep in mind here. Here's a quick example, Facebook's Insights. That's basically from a slide they gave. Basically, there's a system they have developed where they have like 1 million counter updates per second on a 100-node cluster, all HBase. So it's like 10K ops per node, and that's basically the like buttons you can put on your website. And when you someone clicks on it, they track that, write this to a log, and process this with like Scribe, P-Tail, and Puma to aggregate these updates and write this basically out into HBase at the end. So it's like within 30 minutes through the chain, it's in HBase. But after that, basically, you can query and slice and dice any way you really like. So you get like real-time responses, but you have to wait 30 minutes for them to be current. They use counters, so that's another feature of HBase. So again, if you think about where do I store data, think about why just having fields you put into your database. You basically have the counters as well. So you can use the counters in each column to update. And in this case here, you store a counter per domain, per URL, and you leverage the HBase increment, which is an atomic read and modify write operation. Each row in this case is a specific domain, and I have a picture there how this looks like, and each column is a specific counter. Think of it as an OLAP cube you keep live all the time. So you have like a real-time OLAP cube where every single dimension, every single cross, basically, or every single data point is a counter, and you can then update them. So a single click on the like button could easily fan out in 10,000 or 1,000 or 5,000 counter updates, but that's sustainable. So that's the whole idea. So just do this live. Then, so this is how it's done. Basically, they take the reverse domain, for instance, com Cloudera, So everything com Cloudera basically is kept together. So if you have com Cloudera, then block, for example, then you have them separate by domain. But since there's a lot of com domains, you cannot really do it that way. They actually hash that reverse domain with an MD5, which gives a nice distribution across all of the regions. So take the hashed, just the domain name, not the entire URL, just the hashed domain name, and then stick the reverse domain next to it, so you don't have to do a reverse look. I don't know. They can basically scan over and find what it means, that hash, because it's not reversible. So there's the hash, the reverse domain, and then inside they have the information. Or in another table they have the reverse domain, the hashed, so the hashed domain, the reverse domain, and the URL ID, which they track for every URL. And that basically goes into a table, should load in a minute, here it goes, then stores in different column families. There's an hourly column family, a daily column family, and a lifetime column family, because now, in this case, they make less use of compression because they're very small counters. But in this case, column families also have this sort of feature called a predicate delete. So they basically can delete based on timestamps. You remember that versions are timed. So in this case, they set the hourly one to, I don't know, a couple of hours ahead of time, and then the hourly ones get automatically flushed out by the background process. So the daily one, keep it for 7 days, and after 7 days, they get flushed out, and the lifetime one stay there forever, for example, or for a year or 2 years or whatever it is. So you can make use of the column family also in this case to delete data automatically for you. But it's all basically then counters for every possible combination. I mentioned this earlier. There's also OpenTSDB as an example here. In this case, OpenTSDB uses a single column family. So this is a different one. In this case, where the key, if you look at the key there, the row key is metric, a timestamp, and then tags. So instead of having a timestamp first, which gives you this problem of sequential keys again, in this case, OpenTSDB has a couple of thousand metric IDs. They just take the metric ID or metric type, the ID of that metric, then attach the timestamp to it, and then some tags, which they can actually ignore based on this idea of partial key scans, or they can actually look at it and make use of it. And they get periodically rolled up into different ones. So that's basically quite interesting. Here also, some information that should be part of the value is stored in the column qualifier. So they moved some information from the value into the column family. In this case, it's the time delta. So you know basically they have a couple of minutes or so per row, and this is the delta to the timestamp in the key, and some flags telling you what's inside each column, so if it's compressed or what type it is. So it's interesting that you can move this around and just still being able to store the same amount of data. So instead of having this all in a big Ever record or a big JSON record in your value, which you have to pull it back in, parse it, or whatever, you can use this to have a lower cardinality and being able to scan quicker over data because you're moving it up from the column qualifier or column name into the key, depending on how you access the data. Right, so let's wrap this up. You have to either design for read, write, or both, basically. You have to avoid hotspotting. That's just important. And hotspotting is sequential keys, so that goes hand in hand. If you have a hotspot on the server and you can see this from the hits, that's not good. You have to avoid this. Consider using IDs instead of full text. If you can make things, compact things better, it makes more sense because you store a lot of details with it, and if you don't compress, this gets carried around for every single value. So that's an interesting thought. Leverage the column families so that you have basically data that pertains to each other stored in separate column families. So when you query it, you can actually scan faster over smaller column families and then look up data, for example, in a larger one. That's possible. Or shift the details around to the appropriate position. Have composite keys or compound keys where you move things basically into the key or into the column qualifier. So this is like an interesting aspect there. If you don't do this, then you have to go through the entire table, and that's very slow. The schema design is a combination of designing the row keys and the column keys, like this is the sort of field promotion and compound keys. How you segregate the data into column families, and how you choose compression and block sizes, as well as predicate deletes, the time to live for every column family. That's sort of the essential part of schema design, getting this right. Similar techniques as I said, are needed for other systems as well. I mean, you need to have indexes at databases, partition data, and consistent hashing as well. And that's basically, someone like a paper did coin this as denormalization, duplication, and intelligent keys. So you have to often rewrite data differently and use these intelligent keys, which is these compound keys, to make sure that you find the data as quick as possible. And finally, if I go through the questions, there's some contact. There's also, as I said, I'm going to talk at the Hadoop World, and there's another webcast coming up. Let's have a quick look for questions. Okay.
Yes, Lars, we did receive quite a few questions. Are you able to see them in the Q&A box, or would you like me to read them?
No, I'm seeing them. I just have to wait for them to switch over. So secondary indexes, there's work now being done with in combination with coprocessors. So there's definitely more to be developed. That's an exciting area. It's not, as I said, helping you a lot, because a lot of the things you have to do by hand still. But I think coprocessors in combination with either search, like routine integration, or secondary indexes for faster lookups, there's more on the roadmap, definitely for 92 or afterwards. So definitely something coming up. Then the question here is about, there's a lot of emphasis on defining row key dimensions based on access pattern. Is it not a limitation? Yeah, the question is basically, is this a problem basically if you do a full table scan, or if you have to basically do a separate or use the compound keys? I don't think so. I think it's not a limitation. I think it's actually a quite powerful way to structure your data or design your schema. So personally, I don't think it's a limitation. That's more personal, I guess, than anything else. There's a lot of long questions here, which I would have to probably answer afterwards. See if I have a short one. Do we have can we go over? Is that okay? Because it's like an hour now, exactly.
Yes, we can go over a few minutes, so please answer the questions if you're able to, Lars. Thank you.
Yeah, no, fantastic. Yeah, I thought I get cut off or so, maybe because I like to talk and always go over. So let's start from the bottom, because I think that was the first one that came in as well. How does HBase shard regions based on key spaces? It uses some sort of hashing-based function. No, it just does that basically by size. So the size is what drives the actual key space. So if you start with an empty table, you only have one region. If you fill it somewhere, it goes to split it in the middle of it somewhere. So if you go over the maximum size, it splits it in sort of roughly two halves. And just where that size is, based on file sizes, basically, it sort of splits it in the middle somewhere, and then it just keeps growing like this. So it doesn't have it's not really that correct, like how it splits them, like in terms of having exactly the right size, like because it cannot split in the middle of a row. But it just takes the middle of the row keys, basically. If you were to design something that is very heavily tilted, like a region that had a very, very large first row and many, many small other rows, that big one would be carried around for a while. So you can tilt this whole thing a bit and sort of confuse it, but it would keep going and see, oh, it's big, it's too big, so split it, and you get a few smaller ones out, and it will fill up quite quickly again, and it's split it again and again. So it just looks at the overall size of the files inside these directories, and if one of them goes over the maximum size, it starts splitting them. So there's no hashing. It's basically always sorted keys, and it does just by size, and just determines a row where it has to split. So that's basically how it does it. If you use the REST or thrift entry point, will I have a way to use the advanced features such as query batching, caching, put cache that is supported in the Java API directly? Yes, you have. The majority of functions, I think all of them, the new REST API, it was like codename Stargate, has support for filtering and batching and caching. And the new thrift entry point we're working on is called Thrift 2. It's a Jira HBase 1744, I think. It's open for a while. I'm looking for someone to help me finish this. Hint, hint. And that basically introduces the new Thrift 2, exposes the new API that HBase has, because the existing Thrift endpoint is based on an older version of HBase and not really looking like what it should. So the old Thrift, it doesn't have filters and a few other things. The new Thrift will have that. It's a new re-implementation of that one. But REST has, I think, everything as much as I can think of. How big is big when it comes to rows? What size should I consider a ceiling to avoid? If you do not have a boundary, just don't go over, basically. If you don't know how wide your table can get, design your schema to be more narrow. Just split it into multiple rows. Or build for that you say, I only go, I don't know, say 100 columns, and then I go to the next row, or something like this. Because if you do not have a boundary and you have these outliers, they can cause you trouble. If you do know that you always have 1 million columns, but they're just counters, so they're not really that big, then just go for it. That's fine. It's a matter of good judgment there, really. If you don't have a boundary, be careful. But if, in any event, if the row gets close to, a single row can go close to the region size, that's bad. So if you design a row size, aim for at least a dozen or 20 or 30 rows at least should be fitting into a region size. If you're not able to squeeze that further into a single row, then increase the region size, make that higher, and then be able to at least split reasonably. So it's a balance between what you can squish into a row and how much you can put into a region, and you either increase one or the other, or reduce the row, or increase the region size. So. And if you don't have a boundary, then aim for a tall and narrow table. If you don't immediately have a reason for multiple versions in my schema design, is there a reason to set the versions to a value greater than 1? No, definitely not. And if you never write to the same cell, it doesn't cost you anything. So that's quite okay. So you can actually leave it at 3, because if you only hit each cell only once, write only once to it, then you only store it once. If you were to update it a couple of times, you would carry around 2 values you never look at, then definitely reduce it to 1 so you don't have any storage overhead. So depending on your design, either set it to 1 because you know you're writing to it more often, but you're only ever needing 1, or if you don't care, leave it, but then you might carry around some dead weight, so that's definitely interesting. Next one, suppose that I have a user log table with time series keys, okay, and the secondary index another table for these log entries ordered by other criteria in my system. I want to store the last 200 log entries of a user on that index. Should I use value versioning for this, or should I store each log entry ID as a column qualifier? Using the versioning is a sort of a tricky one. In past versions of HBase, using the version for something wasn't really that reliable. If you were to write the same version, the same timestamp more than once with different values, you didn't know which one you would get back. But if you would write the same timestamp with the same value, exactly the same record, it doesn't really matter that much. I know, for example, that a company a large company uses an inbox search now on HBase, and they're using the versioning, for example, with the document ID. So they're using the versioning or the timestamp component as the document ID, pointing back to the actual document in another table, and then have basically the extraction of what, like the word, the context of where that word occurs in the original document as in the value. So the value basically is the detail, while the version is actually another dimension where they use the document ID to index the document that hold that. So both is possible. Depends again on. Yeah, it's a good question. It's more about how much you actually store them, how many versions you have, or how many columns you add to it. Both have the same problem. Both cannot split because they're in the same row. So you end up with the same problem. If you have too many of them, you cannot split that. So I think both is possible, and you can just choose which one you like better. From the top of my head, I don't see a big difference there. There's a lot of emphasis on defining. I had that already. Let me refresh this here. A few more now. So the next thing is, it seems that compound keys can get really long. Does the key length matter? No, as you could. Well, yes and no. Because the key, the one place where this matters is the block index. You remember that the block index holds the starting row key of every of that row that fits into that block. If you were to have very large row keys, then the block index would also grow quite dramatically. So that's the only sort of concern that you have. And in fact, there's also this comes in another way as well, where if you use compression, then you also have a problem that when you compress data, you can actually fit more rows into a H file, which also means that the block index has to store more details, also growing the block index. That combined with the large row keys, that could actually mean a lot of in-memory, because the block index gets loaded into memory, in-memory pressure. So you would have to have a lot of heap to help with this. So don't go overboard with the row key size. Keep it basically in check. Most examples I have seen is reasonable size. You saw the open TSDB there, and even the one from Facebook, just an MD5 and a short domain name. So if it's reasonable like this, it gets compressed quite well, then you should be fine with the block index there as well. But otherwise, if you really put in like, I don't know, a blob or so into the row key, then you have trouble. So yes, you're right. It does matter. Is there a threshold on the size of a cell before it's too big? This goes back to what I mentioned before. It doesn't matter if the row gets too big or a single cell in that row, or if that row only has a single cell. If everything goes by that row, so if the region cannot be split because of that row, because of a single row left, then you have this one big lump there that you cannot handle any different. So cell or row size is the same thing. If you have a very large cell, consider chopping them into multiple cells so that you can have them across multiple either cells or columns, or think about having them in multiple rows. I worked on something that was a HBase blob store where I had this design where I wanted to store, say, videos in HBase. So I chopped them up into pieces and put them into multiple rows. So each row would, for example, hold 100 chunks, 100 columns with, say, a megabyte or 65 meg, whatever you can choose in every single one, in every single column, usually small, so that you can stream them down block by block, and then multiple rows for the entire file, so that you can actually control the width of the table and make it tall, which is good for that. And because the row key is sequential, it's good for sequential read. So streaming is sequential, therefore you can actually access the subsequent blocks quite effectively. So that's a very nice way to design that if it gets too big. So yeah, you must control how large a cell can get. Otherwise, you have to chop them off on the other end, on the other side, on the application layer. Not having timestamp in row key, but having as part of value and having date range scans, is this efficient? the timestamp and the date range scans, basically, if you talk about the scan or get that has a time range with it, has nothing to do with a timestamp in your row key. That's an application idea. So you need to control and say that's a timestamp, and that's how I treat this. The timestamp basically is only important for the store files. So when you say, give me from the last 1 hour, then it can mask out entire files based on when they were written. This has nothing to do with your row key. The row key basically is arbitrary for HBase. It doesn't know there's a timestamp. It just knows that it's a sequential key, and you have to make sure that you can handle this proper, or you don't exceed a single machine, or you have to sort and whatever. So these are two separate concepts, the actual date range scan. If you were to say, yes, it's part of the key, and I'm basically designing my partial key scan using the date range, then it's very efficient, because then you can say they're sequential, but it's bad during the write period when you write it into it. So you better say using the bulk import, prepare the data outside, swap it into HBase, and then do the date range scans inside HBase. That's efficient, highly efficient, in fact, because it's the key. It has the lowest cardinality, highest performance. Multiple tables within the same schema. The question is, you did not touch upon using multiple tables within the same schema. Is this discouraged? No. I often find that the schemas only have one table or so. Often there's only one table in the schema, or two tables or three tables. But I know other peers of mine, they have they have hundreds of tables, and they have I don't know how many, we're talking about tables here, hundreds of tables, and they're just fine with it, and that's okay. I actually, for the book, I transformed a relational database model into a HBase schema, and I could not bring it down to, to say a single table. I only had one single table less than the relational schema, although I did sort of denormalize, but there was no way further to merge them further. So I ended up with, say, a user table and a messaging table or so, or a posts table or so. Sure, you can put them together, but it didn't make sense in this case, so it's totally fine. I mean, having multiple tables and even connecting them in terms of in the application layer, knowing what that means, that's perfectly fine. Sure, there are no real joins or any other way to make sure that they get deleted or so, anything, any relationships. But yeah, that's it. I think, Yasmina, rushed through the questions a bit, but I'm hoping I've covered them all, the ones that were lodged here.
Yes, you've covered all the questions that came in, Lars, and we got so many good questions. Thank you very much.
Yeah, no, definitely. And thank everyone for just being here today, and wherever you are, I wish you the best. If you have any questions, as I said, I hang out on the IRC channel. There's lots of other great guys on the IRC channel, HBase or #HBase on Freenode. Please do ask questions. That's the only way to learn. I mean, that's the way everyone did it, and do not be discouraged. We're there to help or discuss your problems. And we may not have the answer right away, but we're sure interested in how you actually solve the problem. So please do also report back. Otherwise, thanks O'Reilly as well to host this webcast. Really thank you, Yasmina, and everyone else involved for having me here tonight.